Good morning, good afternoon, and good evening, wherever you are. We appreciate you joining us for another webcast with CIQ. I am Zane Hamilton, and I just want to say thank you if you're coming back. We've seen you before. If not, welcome. Go ahead and like and subscribe so we can stay in touch and you can keep up with what we're doing. So today we're going to have a topic and we're going to talk about Fuzzball. I know there's a lot of questions out there about what Fuzzball is, where it came from, what it means. So we have a nice host of people today to bring on. So we have Forrest, Ian, Robert, and Greg. Welcome, guys.
Hello, Zane.
Glad to be back for another week, another webcast. So let's go ahead and just jump into it. And I'm going to ask the question, what is Fuzzball?
So everyone else is being quiet. This is one of those cases where everybody steps back at the line and I'm just hanging out there. But I think I heard Ian start, so I'm going to let...
Well, I was just going to say this whole thing was your idea, Greg, so I think you should pick it off.
Thanks. I was counting on you, buddy. All right. So what is Fuzzball? Fuzzball, as we jokingly call it, is the next generation of high-performance computing, or HPC 2.0. What inspired us to create Fuzzball really had to do with cross-pollination between what we're seeing in terms of capabilities coming out of enterprise, cloud, and hyperscale, and how do we leverage those capabilities in high-performance computing, in traditional high-performance computing architectures. One of the major complexities that we found is that the HPC architecture is leveraging a 28-year-old Beowulf-style architecture. And pretty much every HPC system today is still based on that 28-year-old model. And I'm not ripping on the model in a negative way at all, because it's been incredibly advantageous for us to build large, massively scalable systems and support massive amounts of science through these systems. But they're flat, they're monolithic. And because of this architecture, it's been very difficult to incorporate a lot of the additional kind of capabilities and innovations that's been coming out of enterprise, cloud, and hyperscale. And containers was, kind of the first. And I kind of call containers like Pandora's box, in a matter of speaking, because it was the first time that HPC really looked at what other industries and other sectors of the ecosystem are doing and said, how do we make use of that? There's value there. We could be leveraging that, and how do we use that? So that was really just the first step in terms of modernization and looking at HPC from another lens. So what is Fuzzball? It is a cloud native, cloud hybrid, federated meta orchestration platform for compute-focused workflows and data. That's what it is.
So that's a lot to take in. So I guess, can we break that down a little bit in terms of, like, why is that important and what does that really mean? Again, everybody steps back.
I know.
Forrest just grinning eagerly.
Why is it important? Well, there's a number of reasons. First off, as I kind of alluded to, traditional HPC has been really looking into what are hyperscalers doing, what are clouds doing, what do people need to do in terms of computing in the cloud, and what is enterprise doing, and how do we make good use of these capabilities in high-performance computing. But it definitely doesn't end there. Going back now, maybe about 3 or 4 years ago, I started getting, right when I was really, kind of right in the middle of Singularity and building up containers, I started getting a lot of calls from enterprises who all of a sudden started to see that they are going to be HPC-like consumers. They even said, we need HPC. And how to actually bring HPC into the enterprise is a little tricky. And I heard some really funny quotes about it. One of which was, we're trying to get our system administrators off of SSH, and here you're telling us that all of our users and access into the system requires SSH? No, it's completely the opposite direction from where we're trying to go with our infrastructure. So no, we need a cloud native style system, an API-based system to do this. We need a system that's going to fit in with our existing infrastructure and whatnot. So it was really, it's the HPC legacy architecture that we've been leveraging within the computing industry pervasively again, has been fantastic, but due to its kind of legacy way of operating and whatnot, it just doesn't fit with more modern ways of looking at how to do compute. And that was really what started us going in this direction. I've been talking now so much and just kind of riffing. I don't even remember what the question was, Zane.
So it's really back to, I mean, you said a lot of words in the beginning of what Fuzzball is from a high level. I mean, it obviously integrates with a lot of different things. It has a lot of different parts and pieces, and it can do the orchestration amongst HPC and cloud on-prem, kind of that hybrid cloud model. So it's a lot of things to a lot of people, right? But why is it important?
It's a great one. Robert, Ian, anybody else, Forrest? You guys want to jump in?
So I'll share a little bit of something. One of the big things that makes Fuzzball important is that it's an an automation native solution. We see in HPC that as technology progresses, we have both a need to bring these modern development practices into it. And we also see kind of the practice of HPC itself complexifying in terms of, what workloads we want to be able to run, what pipelines we want to be able to represent. And so Fuzzball on both sides of that gives the opportunity to codify and kind of formalize these different pipelines and stuff, as complex as they are, in a way that can both be easily modified to account for other uses for that data pipeline, as well as easily managed through modern CI/CD practices. So from the user side of Fuzzball, it improves things immensely, as I said, in both the management of high performance computing work, as well as the actual doing and performance of high performance computing work.
Many HPC centers have been asked as well, going back, I think 15-ish years, how do we make use of cloud? And you'll see that many HPC centers have had a very tough time really making good use of cloud resources. A part of that, again, stems right back into that base fundamental architecture being very monolithic and flat. How do you extend that? How do you create some sort of infrastructure that can span between regions, between clusters, between infrastructures? How do we build all of that in such a way that we can pull it all together and then make very informed and intelligent decisions on where should jobs run, right? When we think about where should jobs run, we get to think about some really cool policies, things like not only architecture and resource availability, but cost of computing. Include the data into the model as well. I mean, we've been talking about, in high performance computing, that we need to be thinking about the data as a first class citizen in terms of, scheduling and orchestration. But, we haven't done a very good job up until now on how to do that, right? When we think about data, we have to think about data locality. Where is that data? Data mobility. Can you move that data, and how easy is it to move? At some point, the data just gets too big and you end up with data gravity, which is just too big, so the jobs kind of get sucked into the data. And then you can also have data security policies that pervasively need to be applied across the entire realm of both, movement of data and where is everything going, as well as, sorry, got a call. I just had to go mute, probably spam nowadays. But how do we put all of that into a policy and think about that from a meta orchestration federated perspective? And how do we pull all of that and unite all of those resources together in a way that makes sense? So we haven't had the ability to make those sorts of decisions before. So that's super cool. And again, I just want to double on what Forrest said regarding the diversity of jobs and workflows has been massively expanding. HPC used to be something very specific with regards to tightly coupled parallel applications, and anything that was not tightly coupled parallel applications, some people wouldn't even call it HPC. Now HPC is pretty much anything that needs to run fast. And whether it's a single process, single thread, or you're scaling out, or you're doing some sort of parallel training, or you have a service that's running, that's doing inferencing, or some sort of data stream or pipelining of data and ingestion of that, and being able to compute in real time on what's, all of this is now high performance computing. So the scope and realm of what is high performance computing has increased massively. And our traditional HPC architectures just are not very good at dealing with this now.
It's interesting because whenever I used to work for in the airline industry, one of the things that they did a lot of every month, they had to come up with a schedule for planes, and it had to make sense for where planes were, where the crews were, how much the fuel was, how efficient the plane was. And it was something they typically just ran on, it used to just be on a bunch of HP UX boxes, and then it became kind of a small Linux cluster. But those jobs would run for 30, 40 days until they were optimized enough. But it sounds like that would be a really good use case for enterprise IT actually using an HPC type environment. And is that something that Fuzzball would help with?
Yeah, absolutely. And again, because, when we started thinking about how do we modernize high performance computing, the first stabs that we took, when we were first thinking about this, it was, what do we need to put on top of traditional HPC? What capabilities, what APIs? And it was very difficult because we're basically, I know I'm going to get backlash for this, but we're trying to put a saddle on a cow. It's not exactly the same thing because it's more like putting a saddle on a high performance computing race car. Maybe that's a better analogy in this particular case, but it became overly complicated. It became full of duct tape and shoelace to pull everything together. And really what we needed to do is think about this from the ground up. So we went the other direction. We started with Kubernetes and we said, what do we need to do to make Kubernetes good at this sort of thing? And again, maybe that's a little bit more like putting the saddle on the cow now. It's the wrong tool for the job, especially when we're talking about high performance computing and trying to run that through a architecture that was designed for microservices. It was not a good fit. We had to come to the rationalization and the understanding that we have to rebuild this. We have to think about this from the ground up and almost reinvent high performance computing and the architecture for high performance computing into something that is, again, I love this string of buzzwords: cloud native, cloud hybrid, federated, meta orchestration for performance critical and performance intensive workflows, jobs, and data. And that's what we basically set out to solve. And it's a big problem to solve, to be honest. And that's why we were founded. That's why we were funded to create that. And we've been working on it for about 2 years now. It's been fairly hush-hush in terms of what it is we've been building. And so we're just coming out to market. Now we're just starting to do some announcements. We're letting this out in terms of what we've been working on. We have a number of organizations that are currently in proof of concepts right now, early access, beta users. And we are going to be releasing this around late Q2, maybe early Q3, and bringing this GA. In the meantime, we are working with early use cases and early individuals and organizations who want to be part of this, want to see what it is, and have a strategic interest in terms of bringing ideas back into the platform and really helping us to make sure that we are solving all of these problems. And the use case that you just described, Zane, is massive. And that's just a perfect example of how these sorts of architectures can now support organizations who were never doing high performance computing before, but all of a sudden are looking at HPC and thinking of themselves as being HPC consumers.
Sure. Let's say we got a question that popped up, but I wanted to pick on Robert before we answer that question just real quick. I know that you talk to a lot of different companies, a lot of different people out there. What are the dominant use cases that you're running across right now that are people that are interested in Fuzzball? What are they trying to solve? What are those use cases they're trying to solve with Fuzzball today?
So it's very varied, like Greg was saying. So it's all the way from traditional high performance computing, which we do extremely well and can do on any hardware and any cloud now, and tie that together into one unified resource. But it's also machine learning, AI, starting to come into play in a lot of different places. And that's where the flexibility of the solution really comes into play more. So that's what we're starting to see more and more, even down to running, Jupyter notebooks from the HPC resources, VDI. We're starting to run into a lot more persistent jobs as well. So Yeah, I mean it's flexible enough to solve all those varied problems at bare metal speed when it's deployed on hardware itself, but have that flexibility to be dynamic in the clouds as well. So yeah, I mean that's what we're seeing over and over again.
Excellent. All right, so Tron, your question is, what are the components or technologies in Fuzzball? So I think that's an interesting question, and it could be a big one.
Yeah. So
Ian, there you go.
This might take a second, but we can kind of start at the base level. So we have several kind of layers, which is a typical way of describing software stacks, to what we would call like a full Fuzzball cluster. So the first level is Fuzzball Substrate, which is really just a single node resource manager that is able to spawn containers with a leasing model that allocates resources to containers based off of an API. So that allows us to have a set of nodes, manage all the resources on the nodes with a higher level orchestration tool, and run containers on all of those nodes in order to run basically any application stack that is suitable for the hardware resources available for that node. Just to give a little bit of a parallel, for traditional HPC with like a batch scheduler, if you're familiar with container technologies like Aptainer or others that are available, what you would typically do in those environments is have a batch scheduler that spawns a process running as your user on that node, and then you have that process call out to like a CLI tool that spawns your container. Fuzzball Substrate actually just takes the direct job request essentially for running a container and immediately spawns that user container for us. So we don't have to have another tool in the middle. So this is part of what Greg was talking about reducing the complexity in the stack and building it from the ground up so that we don't have as many integration points and we can manage everything basically from a single control plane. So on top of Fuzzball Substrate is what we call Fuzzball Orchestrate, and that's actually a set of microservices that run in Kubernetes. So we use a Kubernetes cluster to manage our microservice stack because Kubernetes is a very good tool for that job. We could use another orchestration framework for running microservices if we wanted to, but that's what we chose because it's best in class at the moment, at least in our opinion. And that will basically allow us to manage the inventory of compute nodes that are available in the cluster. So we have a set of control plane nodes that run our Kubernetes cluster with all of our microservices on top of it that manage our compute nodes. Then we have our compute nodes that just run Fuzzball Substrate. So we basically can start up a container on Fuzzball Substrate with a certain set of resources and then get out of the way and let it run as it would normally run for any other type of kind of batch work that you might be familiar with. So with that Fuzzball Orchestrate stack, we can do things like manage container images, run what Forest will show us with our workload definitions, where we execute a directed acyclic graph of steps in order to complete a computing pipeline, and do other things like manage data or manage policies around users being able to use certain resources or resource quotas, things like that. So that's kind of the second level of the stack. And then out on top of that, we have I think we called it Fuzzball Federate. So that layer is essentially taking all of our Fuzzball Orchestrate clusters and connecting them together so we can make high-level decisions about how we want to schedule workflows. So at the Fuzzball Orchestrate level, we're doing things like making decisions about how we schedule directly to nodes, whereas at the Fuzzball Federate level, we're making decisions about how we schedule to data centers, essentially. So we might have several different clusters in several different locations, maybe some on-prem, maybe some in the cloud, and we want to make decisions about which cluster or data center is the best to run a particular workflow based off of different types of suitability, whether that's resource like amounts, or if it's actually like resource classifications or overall policy about what resources that user is allowed to access. So I think Greg, you just pulled up a slide, or someone did. Would you like to talk through that slide a little bit? You do this a little bit more than I do, from the slides perspective, at least.
You were talking already to this, so I just wanted to put up the visual. This is kind of what a federated meta orchestration platform using Fuzzball would look like, where you basically have workflows coming into this federation layer, and this is where you can make policy decisions based on things like resource and architecture availability, as I was saying before, cost, as well as where's the data gravity, data mobility, data security. So we can actually say, so for example, if a workflow comes in and this workflow is requiring data that exists in, let's say, S3, we can make the decision. Do we want to run this workflow up in AWS so we don't, in a particular availability region or zone, so we don't have to incur any sort of egress cost of moving that data? But now we're actually incurring some sort of cost to actually run the compute. If we move the data to an on-premise cluster, maybe in that particular case, we'd actually get better performance. Maybe it would be less expensive, but we get this ability now that we can start thinking about it at this level. And to kind of go back a little bit in terms of what Ian was describing in terms of components and what the architecture looks like, you'll see if you're familiar with traditional HPC, this is kind of like a traditional HPC compute cluster. You got some sort of base provisioning, you've got a small operating system, and you got, in this case, Fuzzball substrate running across all of your compute nodes. This could be tens, this could be thousands of compute nodes. On this side, you're going to end up with some sort of scratch file system, parallel file system, Lustre, GPFS, or just a high-performance NFS type system to share out data and volumes across this compute cluster. Now, as Ian was saying, Fuzzball Orchestrate is a microservice platform in itself. So we're going to want to run it on top of some sort of microservice platform, like architecture or service provider, like Kubernetes. And in this particular case, this is how we would ingest a workflow via an API here in Fuzzball Orchestrate. This workflow will come in, we'll be able to basically ingress data as the workflow defines, ingress data, create the volumes, run the job pipeline, and then egress any data. And what that means is this data lake kind of becomes the home directory storage of what we're using today as home directory storage and high performance computing. We still need, as I said, that scratch file system that's running here because we're running a bunch of volumes and we're shuffling data across a bunch of nodes. So we need something highly performant here. But in terms of that persistent storage, we don't need to use some sort of very expensive, enterprise grade NFS home directory storage, which is what we have been using. Now we can use a data lake. And the nice thing about the data lake, going back to this slide, is data lakes are actually, and object stores, are much better at doing distributed and redundancy and spreading out across geographies. So this gives us the ability to leverage that data store as a distributed data lake, in a matter of speaking. And now we can run jobs anywhere. And we are working with partners as well in terms of organizations and providers of a distributed data lake and to figure out what's the best way of doing this. And maybe it makes sense, while I have some slides up, if nobody minds me standing on my soapbox a little bit longer, to talk a little bit about the workflows. And I think, Forrest, you have some demonstrations that we're going to be running. But just to give a quick introduction in terms of what is in a workflow and how a workflow looks, we basically need to support 3 different aspects in a workflow. So a workflow basically is going to be consisting of you need to define your data and volumes, and you need to describe your job pipeline. In this case, the volume, we're going to set up a volume named V1. It'll be an ephemeral volume. We'll have some ingress data we will pre-populate this volume with, and Fuzzball will automatically manage the movement of this data. It'll manage the caching of this data, so subsequent jobs that require the same data will land on the same resources and be able to leverage that. At the end of the job pipeline, we'll be able to egress things that we want to persist and retain after running this job, or the workflow, excuse me. Now, jobs is basically, it is a full acyclic graph of individual jobs. Each job has a number of attributes associated with it. So NCL, just to jump at the end, requires UFS. UFS requires UNTAR. And UNTAR has no requirements, so that one will run first. You'll see it's going to run, every job is going to run completely within a container. So the first thing we're going to do is we're going to pull the Docker Alpine, or the Alpine container out of Docker. We're going to basically spin up that container, and we're going to run this command inside of that container. When we spin up this container, we're also going to mount up V1, this volume, inside that container at /data. Now, once this is done, which is basically a data prep, we're going to untar what we downloaded up here. Then we're going to run the UFS weather model. Now, this is an MPI job, so we're going to run it across 128 nodes. We're going to do the complete MPI wire up using OpenMPI. So historically, with running containers and MPI on high performance computing systems, you're typically running in like a hybrid environment where you have part of the MPI outside the container, part of the MPI inside the container. In this particular case, we're actually running 100% within the container. So this container would basically run across 128 nodes. If you're running InfiniBand, that will automatically be managed and leveraged. And we're going to run this command within it. We're going to start that command in this directory. Notice it's in /rundir, and that's because that's where we're mounting volume 1, which we, again, from up here, at /rundir. And then NCL is a quick visualization program that we're going to basically run to basically take the output of this and now turn that into a couple images. And then at the very end of this job, we're going to take those 2 images, and here you can see we're just putting them to a local file system, but we can very easily upload that into something like S3, where it can be visualized globally or elsewhere. We have a graphical environment that we're working on as well that will be released shortly, or when we release Fuzzball. And this graphical environment can be used to both create and make workflows, but it can also be used to templatize workflows such that each workflow now becomes, in a matter of speaking, a very simple compute-focused application that you can now create almost like a web form to go create an application to go run workflows where the inputs, the outputs, or any other templates that you put into that workflow will be automatically replaced with the contents of what's in that web form. So there's a lot of kind of options and things you can do with a system like this. And keep in mind, even when we go up to this level, that workflow will come in and we will figure out where it makes the most sense to run it based on the policies that the organization requires and has set forth. One other quick note, there is no SSH anywhere in this system. So all of this is going over APIs that are governed by IAM policies across the entire platform. So every aspect of this can be secured tightly, and system administrators and, again, organizational policies can define what is allowed to run, where is it allowed to run, how is it allowed to run, and what are users or groups of users allowed to do with that. So I've been talking for a while. Anything else anybody wants to add to that?
Yep. So from the workflow perspective, that file that you showed, that's what a user would create. At some point, there will be the GUI to help them create that. So that's user kind of the experience. And I know Forrest is going to show us that in a little bit, but from an administrative standpoint and setting up those policies for where things land, how hard is that? And how does that, from an administrative perspective, what does that look like?
Ian, you want to take that?
Yeah. So basically, we have sets of curated policies where, like, for initial deployments and proof of concepts, we're working with organizations to understand what their needs are, and then building the policies with them in order to properly, set user roles and manage resource access and do things like that. The policy system is very expressive, which means you can do a lot with it, but it also means that there's a lot there to document and to understand. And so it's basically a learning process where we want to set up specific rules of policies so that it's easy for like a standard deployment to work how administrators would expect based off of what they need. And then if they want to dig in and do very specific things and allow very specific things to happen, they can go ahead and do that as well. So it's really about making sure the common use case or for the common deployments that administrators want to make, that is straightforward, and you get kind of the roles and abilities that you would expect. And if they want to go on and tweak things, then they have a very expressive system to do that, so they can get it exactly as they'd like.
Excellent. Thank you. So now we are right at half an hour. Forrest, I want to leave you enough time to make sure that you get to show us what you brought. So if you want to go ahead and show us your demo.
Sounds good, everyone. I will go ahead. Sorry. I'll go ahead and share my demo or my terminal screen here really quickly. Give me just one moment.
Yeah, while he's firing that up, we got a couple of other questions, and there's So the first one, what about a migration path from existing end users from a traditional HPC environment? What does that look like? That's probably another question for Ian, Greg.
Yeah, so the migration path would really be about using either a proof of concept environment that you might set up. So you would like set up a side environment from your production and give users access to that to start to test it, or you would give work with us and give users access to our cloud deployments of Fuzzball so that they can get familiar with the platform and get a feel for how it works from a user aspect. From a like administrator managing infrastructure, it would be a hard switch in terms of having your nodes be managed by Fuzzball versus whatever your current infrastructure is. From a user aspect, there's definitely paths to migration where users can get familiar with the platform, understand how the workflows work, and even use the same containers that they're currently using if they're using Aptainer containers on the Fuzzball platform as a part of their workflows that Forrest will demonstrate and get familiar with the system.
Great. And the other one real quick. So yes, Fuzzball is cloud vendor agnostic. It doesn't really matter. But whenever you say IAM, Greg, policies, it sounds like an AWS term. I know we're not talking about AWS terms.
Yeah, sorry about that. We are using the same acronym for identity and access management, but it is a policy that we have created specifically for Fuzzball. It is not related to AWS IAM at all.
However,
just in name.
However, I would add that one of the design principles is that the end user and the administrator have the exact same experience, whether it's in AWS, GCP, Azure, on-premise, connected as a unified platform. It does not matter. That IAM policies do transfer no matter where they're running them, and that end user and admin experience will be unified. That's extremely important to what we're trying to accomplish.
Thanks, Robert. Thanks for the questions. All right, Forrest, back to you.
All right, we're good to go. All right, if everyone can see that all right, I'll go ahead and start into this. So I'm here on my command line. As Greg mentioned, I'm not SSH'd anything. I've just gone ahead and done the Fuzzball login process, which is a web-based flow essentially. So I'm going to go ahead and run a couple of workflows here. The first is going to do, it's going to run Jupyter Notebook, and I'm going to show you how you can interact with that while it's running on a compute node. And then the second we're going to do is more traditional batch processing with a molecular dynamics suite called LAMPS. So I'll go ahead and start this workflow off here. And here on the CLI, we do Fuzzball workflow start. And then I provide the name of the workflow and my account information. So we'll do Jupyter AI training. And we'll just say this is the first one of those we're going to run. And we'll specify the path to the workflow YAML file that we're going to be using that contains the workflow that Fuzzball is going to run.
Forrest,
we'll go ahead and start that off.
Can you increase the font a little bit? Sorry about that.
Yes. Does that look better?
Yeah, if you could do one more, I think that'd be great.
Okay. There we go. Okay, so you'll see that this workflow is now started. We can go ahead and do Fuzzball workflow status, and then we'll watch this to watch it as it runs. You can see we have, actually, 1 second. I'm going to decrease that because that's going to want to print.
Yeah, we do need a certain amount of character width in order to display all the information in like the table describing the components of the workflow as they're running. So I'm not sure if you can widen your terminal for us that you're sharing, or if we just need to lower the size of the font.
This is as wide as it goes. So I'll lower the font a little bit. You can see that a little bit better. Does that still look good on everyone else's end? Cool. We're waiting for this to start anyway, so really quickly, let me just clear my terminal really quickly. So just to explain what exactly we're looking at here, you'll see this wraps around a little bit, but this last column is basically just any errors that happen with any of these workflow components as they run. We have 3 different things represented here: workflow, volume, image, job. Workflow over here is just kind of giving the actual status of the entire workflow itself. Volume and image are giving the status of the setup of the data volume that's going to be attached to this workflow that it's going to be able to use to store data in or bring data out of when the workflow is finished, and also persist data in between workflow jobs. So they can each access that same data that's been pulled in to this workflow or generated from somewhere else in it. You'll see that we have also an image here that's being pulled. This is coming down from a GitLab registry. So I've provided some secrets inside of this workflow that are essentially my credentials to access this GitLab registry, which is what gives me the ability to be able to pull that container down, because otherwise wouldn't have access. You can also see one job here, and that's the job that here in a moment I'm going to do some stuff with so that I can get access to the Jupyter notebook that's running in it. At the moment, as we run status, and as mentioned, we can watch this, but with the width of the terminal, it'll print a little weird. So for clarity, I'm just going to keep it like this. You can see that at the moment, this job is basically just sitting here pending. What's going on is that we're essentially provisioning this node right now so that we can launch this job here on it and be able to have access to it within this notebook that I'm going to show you in a moment. So we're essentially just waiting for this job to start. While we're waiting, do we want to go through the workflow definition that backs this really quickly?
I'll just jump in and say that the reason why this is taking some time to start is because on the back end, we're actually provisioning a VM within a cloud provider in order to run this workflow based off of the resource constraints specified as a part of the workflow definition. So when you show the workflow definition, we'll see the resource constraints. So I think we should do that next. But I just want to say that, like, if we're working with like a static node pool of like on-premise infrastructure, it'll start running immediately unless there is like a queue for those nodes.
Cool. Thank you, Ian. Very good to point out there. So really quickly, I'll take you through what this workflow definition here looks like. So you can see this is basically just a flat YAML file. And as Greg kind of showed with that example earlier, we have a few different sections. We have basically just a version header that tells what version of our DSL this is based on. And then we have a list of jobs that are going to be executed when this workflow runs. In this case, we basically just have one job, and that's named Jupyter. But you can see we have a bunch of different things inside of this job that are being done in order to properly set it up. First off, I'm going to kind of go out of order here. First off, we have the container image that this job is being pulled from, and that is landing on that compute node, and that the actual computational job here is being run inside of. You can see, as I mentioned, this is pulling from GitLab. So this is just a custom container that I've put together that has everything we need in order to do the notebook that we're going to do in a second in it. You can see I've also provided some secrets and basically some credentials there. And I've also stored some of those secrets inside of our Fuzzball cluster for easy templating when that workflow runs. So I don't have to manage those credentials in an unsafe manner myself, and for ease of use. You'll also see that after the image, we have this command here. This command is what's going to actually run inside this container when it all starts up on the node. So in this case, we're basically just launching a Jupyter Notebook instance on port 8888 with a couple of other options there. We also do a few things to kind of set up the other parts of the environment here. We have some policies that are set. In this case, we basically just have a timeout policy. That means that this workflow will stop automatically after 30 minutes. And then we also have some environmental variables here that'll be injected into this container so that anything running inside the container can access them as well. You'll see that we are mounting some type of data to this. I'll move down here. You'll notice that in addition to the jobs section, we have a volume section. This is actually allowing you to bring up a storage place, as I mentioned, for workflows to use. So this is an ephemeral type volume. This will disappear and basically only be active for the lifetime of this workflow. So this is sort of a scratch space to bring things into and use as a space for jobs to operate on the same data within. So you can see we set that volume up there, and then we attach it to this job right here at this location, which I'll show you in just a moment once we actually hop into this notebook. And then here we also have the resource counts that this is going to be looking for. So as we've discussed, this allows you to kind of set on the fly exactly what resources you want available to a workflow. And then the scheduler will do all the logic in order to figure out where the best place for that workflow to run is. So you can see we have CPU, memory, and devices here. CPU allows you to specify the number of cores that you want, and then how you want those cores to be kind of selected from the compute node. In this case, we're doing a NUMA affinity, so this will minimize the number of cores onto as few, or will not minimize the number of cores. It will minimize the number of NUMA nodes that are being used on a given compute node if it supports a NUMA architecture. So that's efficient. That's trying to land things all in a space that all those cores are going to be able to access the same memory location with NUMA. But we have other affinities that you can choose that are a little bit more broad and less granular there. We also specify the amount of memory that we want in GB bytes. So that's going to give us 12 GB bytes worth of RAM that this workflow will be able to use. And then we also specify that we want an NVIDIA GPU through this devices specification. So this basically is just going to reach out and look for a node that says it has a GPU attached to it, and then serve that back to us so we can use that in our workflow. I'm going to go ahead and, as this is provisioning live, sometimes it can take a little bit of a variable amount of time for the node to come up. So I'll status this again, and hopefully we'll see that this job is started. And that means that the node is brought up, but it hasn't yet, so we're waiting on this. This typically takes, I would say, about 5 to 10 minutes or so. So we'll probably be waiting on this for a second longer. But it shouldn't be too awful much longer, I hope.
I can jump in on this question while we're waiting for that.
Cool.
So basically, if you go back, and I don't have the slides up right now, if you have put a cluster in AWS, for example, we could be leveraging that cluster. If you have a cluster that's on-prem, you can run a federation or Fuzzball federate on top of both of those. And then Fuzzball federate will decide which cluster it goes to. There is no infrastructure within this demo that is like a cloud SaaS type solution. Although we have been asked to do this. So this is going to come online where we are going to be hosting a Fuzzball cloud for people if they wish to run on top of that. And then we would basically make determinations in terms of where things would run, again, based on policy. But for the moment, it is going to wherever Fuzzball is currently installed.
Thank you, Greg.
And it looks like we are still waiting on this. So
It's always for a live demo, huh?
Mm-hmm. Of course, my tests, it was 5 minutes or so reliably, but we'll see how long this ends up going for here.
Murphy's Law.
There is an option as well that we've used in the past, and we're not doing it now apparently, where you can actually provision resources to be spinning and be up and running kind of on standby. Most organizations, when we're talking about the cloud compute side of this, really like to keep all of their costs down to a minimum. And that's one of the nice things about cloud. So a lot of organizations that we're talking to, especially if they have multiple resources, they've got an on-prem resource, they've got a cloud resource. The on-prem resource is kind of statically defined. It already exists. So typically, you're going to have all of that running and available and ready. On the other side of this, if you have a cloud side, a cloud cluster, you don't want to keep any compute nodes running just for the sake of keeping them running. So typically that will automatically shrink down to just the bare minimal requirements for Fuzzball to operate, which is really just that Kubernetes cluster. And we'd sit on top of like EKS or whatever you happen to be using for your Kubernetes infrastructure up in the cloud. We would just sit on top of that and run there. And then as soon as a job comes in, we would automatically provision a new instance, a new cloud instance for that job, meeting the needs and specification of the workflow coming in and whatnot. So hopefully that answers the question. And I see that it is started, so I'm going to stop blabbling and hand the mic back over to Forrest.
Yeah, so we're good to go. That node is provisioned. As you can see by the status over here, listing is started. That means that this job is actively running on the provision node. That we should be able to access it and do some different things with it. So the first thing that I need to do in order to get the link and token that I need in order to access this Jupyter notebook is just to open up the log of this workflow really quickly. And you can see we have some output there. We're going to be looking at this namely. And because this is running at a separate data center, in a public cloud provider, I actually have to port forward this workflow back to my laptop here in order to be able to get onto this notebook that's being run here. So I'll just go ahead and do fuzzball workflow port forward, and then we'll provide the name of the job, and then the name of, the name of the workflow, and I'll provide the name of the job in that workflow that we want to connect to, and then a local and remote port to forward from. We'll run this, and you'll see we're listening. I'm going to go ahead and switch over my sharing really quickly so you can more easily see what I'm doing here.
It's important to bring up that's not an SSH port forward either. You get asked that question quite often whenever Forrest is going through this. It's actually, I'll probably say it wrong, Greg. It's API TLS.
So we're using gRPC as the foundation of our API, and so we can use a streaming RPC setup to pass the data from like your container process all the way across a couple proxies when we do like these federated setups to your terminal. So that's how port forward works when Forrest shows something like execing into the container as well. That'll also be done in the same way. So we're not opening up SSH ports to the node itself. We're doing everything over our API.
Thanks, Ian.
I think it's also...
oh, sorry, go ahead.
I think it's also cool to note as well is that port forward, right now we're using that for Jupyter, but you could use that for pretty much anything. I mean, we have customers that are using that for remote desktop, accelerated desktop visualization and VDI. You can use it for, all sorts of stuff. Anything that does network I/O access, you can actually do that port forward, and that gRPC API, the streaming API, gives us the ability to not only do ports, but we can also do sudo TTY. So you can actually get a shell in one of the containers that, from a user perspective, you may not even know if that's running up in AWS or what availability zone it's running in AWS, or is that running on-prem. All of that is completely transparent, but it all just works, bringing it right back to the user's workstation exactly as they would expect. And all of this can also hide behind a graphical environment, which we're working on right now to simplify.
And one thing I'll add is, because it's through our API, this directly interacts with our IAM system. So if an administrator wants, they can completely turn off port forwarding or access to running containers and put a curtain up, essentially. So if you have like requirements around what machines can view like the data being operated on by a container, you could completely turn off these types of features and only allow workflow submission and nothing else. Forrest, you're probably ready, but real quick, I think we should answer Stefano's question. So in order to get started, we need a K8s cluster, compute nodes, which could, if you want, this isn't optimal for like performance or context switching, we could have those within the K8s cluster, but outside is better. A storage system that allows all of the compute nodes to have the same view of data, and that's all you need to get started. So if you're interested in looking at more, I would have you talk to Robert about a potential POC or anything like that. Yeah, go ahead, Forrest.
Cool. So just to make sure that we're all clear on exactly what we're doing here, we've had this workflow that's ran here. I've gone ahead and got the log from it, and then I've gone ahead and port forwarded that workflow back to my laptop here. When I control click this, that's probably going to bring it up twice. Close the old one. When I control click that, you see that it brings up here in my web browser the homepage of this Jupyter notebook. This is a full interface into this compute node that I can basically use for whatever I want to do in Jupyter. I'll go ahead in this case and upload a notebook that I have from my local machine here, and then we'll go ahead and run that. So we have a PyTorch demo notebook here. Oops. Sorry, I accidentally touched something. We'll go ahead and push upload there, and you'll see that that has gone ahead and uploaded. So this is now sitting here on this compute node. I'll go ahead and click this to open it. Well, first off, I'll grab a terminal into this so we can show you something else I'm about to do here in a moment. But I'll go ahead and open this up, and we'll see that this notebook opens as you would expect. This is a terminal that's sitting on that compute node that we were just on. So I'll do NVIDIA SMI, so you can see that we have a GPU available as we're going to be doing some GPU-based AI training here. I'll also swap back over to this really quickly and show you our empty data directory. This is where that volume that we attached to the workflow was put on, or was landed inside of the container. So this can be written to, and we can persist data between workflow jobs and such like that inside this directory. So I'll go over here and we'll take a look at this notebook that we have. This is basically just a PyTorch tutorial notebook that does some AI training. I'll go ahead and run through the code in it. We'll do some quick imports. This is going to do, as we discussed, Fuzzball has a very robust ingress system that allows you to bring in data from different places and object storages. It also supports custom data movement, so data movement with inside jobs themselves, if that's something that you need to do. We'll go ahead and run this, and we'll see that this is going to hopefully download a little faster than that, because it was downloading faster earlier. But if not, I believe I've, we'll give that a second. Yeah, it might be going faster than we think. All right, so yeah, like I said, this download will progress. I was expecting this to go faster than it is, because it did in all my testing.
Demoing in the cloud is always fun.
Yeah, like I said, this should be like a quarter of the way done by now or so. So we'll give this a moment. Maybe we have another question or something we can discuss in the meantime. Anything like that, this will take a few moments.
Yes, this is kind of a statement and then a question. So it's talking about provisioning. Sounds like setting up Fuzzball could be tricky, but the next question that follows that is, can a tool like Werewolf help with that? There you are. Or are there existing CloudFormation templates to assist with that provisioning?
So this is not a talk on Werewolf, but thank you for bringing this up because it's super important. One of the things about Werewolf that allows, that really facilitates how how you would basically use Werewolf to stand up a custom resource is being able to pull in. I think, by the way, I think I'm hidden behind the icon there. I don't know if
I thought that's just what you looked
there
like.
we go. Thanks, Ian. One of the I completely lost my train of thought now. Because Werewolf basically takes OCI-based containers and we provision them out to bare metal, it's very easy for us to basically set up things like node images, things like even Kubernetes images, and be able to splat that out to bare metal hardware, spin that up in such a way that we can facilitate how it basically sets up, these resources. So yes, there is a significant amount to actually set up a Fuzzball cluster, but aside from the Kubernetes piece, there's nothing that you would expect that is more than a traditional HPC system. You still have shared file system. You still have to deal with the network, InfiniBand, provisioning out those resources. And again, Werewolf will help with that. We will be offering images for Fuzzball that you can just basically download, import those into Werewolf, and then blast those out to compute nodes. So if you've got 1,000+ compute nodes, Werewolf will be able to provision those out very, very efficiently. And get you going with Fuzzball, at least on the compute section of that cluster, very easily. For the resource management of that cluster, you will have to have a Kubernetes setup. As Ian mentioned earlier, it does not have to be in direct proximity. As a matter of fact, we do have one use case at an HPC center right now going on where they basically stood up the Fuzzball microservices, Fuzzball orchestrate, basically within a VMware resource. So basically, they're within IT's VMware setup. They basically installed, they had Kubernetes running there. They installed all of the Fuzzball requirements for orchestrate there, and then they basically brought in Substrate on a system that's even on a different routed network from that VMware system, and they're basically able to bring up the compute nodes over there. And then the compute nodes are talking to the orchestrate cluster that's back over in VMware. So it's kind of a cool way of being able to build this. But if you do already have a Kubernetes cluster, we can definitely leverage that. I'm looking up now at the screen, and it looks like, did we get past?
We did, yeah. It started moving a lot faster than it was there, so we're good to go.
Demos in the cloud, yay.
Yeah, we'll continue on with this. We'll show a couple of those training images that we just downloaded here so we can have a little bit of an idea of what our data set looks like. We'll go ahead and actually set up our neural net that we're going to be using for this. Run some of the other code that we need. And then, as I mentioned, this is sitting on a GPU node. You may have noticed in the workflow that I showed there, I was specifying that I wanted an NVIDIA GPU. And as I indicated over here, I can also use NVIDIA SMI, and we have one of these Tesla T4s on this node. I'll go ahead and start this code right here, which is actually going to train this neural net on that GPU. So we can see, one moment. Going to reshare just my browser. There we go. Okay, so this should begin giving us some output here in just a second. There we go. So you can see this is starting to print the status of training. We have a loss value over here that basically represents how well trained our model is. And we're going to do 2 epochs. So we'll see this stop here in about a minute or so. If I move over here, I can do NVIDIA SMI again. You'll notice that because of quirks of how containers work, we don't see exactly what process is running here, but we do have an indication that there is a process running here because we no longer see it, there's none running. And we also have 1142 MB of GPU memory taken up, which is essentially our model sitting on that GPU. So we move back over here. We'll run this one more time. You can see our utilization over here is at 24%, indicating that this GPU is actually running at the moment. And you can see that this is still training on that. So we'll give this a few moments. While this finishes, we'll go over here. Yeah. So you can see that from this kind of top level view of everything, if I go into the data directory, within this code, that's essentially where I told this to download to. So this is now in that volume that we set up at the start of this. And you can see that data that we spent a little bit ingressing there from within our code. In just a moment, there we go, we'll finish training, so that's done. We'll go ahead and save off the trained model that we just worked with. And if we go back over here, you'll see that that model right there is available. And I can also do things like download. I'm not sure if you can actually see this, but I'm able to download that directly to my laptop from this interface as well. So if I want to move things around there, I can do that. If we go over here, we'll show a few images from the test set. So we've got a cat, a ship, and a plane there. We'll do some code really quickly to get these test set images to the model. And then we'll go ahead and actually run essentially some live inference over our test data set. So you can see our model has predicted that this is a cat, a car, a ship, and a plane, which is not too bad for something pretty basic like this. And then we'll also go ahead and run the neural net that we just trained over the entire model. So we'll get kind of some information on how exactly it is, how accurate the model is over the entire data set in general. You can see it's about 55% accurate. And we'll go ahead and run this as well, which will give us kind of the output per category that's in the CIFAR 10 data set we're using to train this. So you can see that for each one of these different categories, we have a value for exactly how well the model was able to recognize that type of object. And yeah, once again, this is all running via Fuzzball workflow. This is sitting on a node at a major cloud provider's data center. And you can see that we're able to, just with a container that I've created, instantly bring it up and then upload material and stuff from my own laptop. I could ingress things in from the internet to it. But you can see essentially here I'm able to open this workflow, open the Jupyter notebook inside of it, and then upload something from my own laptop and be able to run that effectively, using a GPU as well. So that's Jupyter Notebook through Fuzzball.
Excellent. We're kind of getting close to time here, guys, but there is one question that I get quite often, Greg, and I'm gonna direct this one to you because it is something that gets asked pretty much every time I talk about Fuzzball, and is, why is it named Fuzzball? Where did the name come from? What inspired it?
That should be to Robert.
Yeah, that should be to Robert.
Is it Robert?
Robert named Fuzzball.
It was essentially a play on, as Greg said earlier, the Pandora's box to get us to Fuzzball was containers and Singularity that Greg founded is a piece of that. Obviously, Fuzzball is a singularity as well, but in string theory, right? So, and then also it ties together everything into one. And that's really what we're doing here, right? Tying together multiple different resources into one, and giving end users and admins an extremely efficient and similar experience across everything, as well as providing applications the ability to have freedom to run wherever it is best for the applications to run. This is what's real important about Fuzzball. It gives the power back to the researcher, power back to the administrators of those researchers, and gives them the ability to really do the science that they want to do. And that's really what we want to do, is really enable those folks to do what they do great. At the end of the day, that's really where Fuzzball came from, and it's really our ethos of what we're trying to do as a company.
I'd only add, I think Robert nailed it. I'd only add as well, we've got the cutest little mascot too. It's a little fuzzy that you'll see here come out here shortly. So
that's awesome. So yeah, Tron's asking how can he get his hands on Fuzzball? That's going to be probably a me question. So I will reach out to you, Tron, and I will work with you, and we will figure out how to get you access to Fuzzball. So if we don't have your contact info, Tron, please someone reach out to Tron and get that from him if we can, without making it too public. So I appreciate you guys. I know we are actually about a minute over. Thanks for the time today. We appreciate you joining us. Again, remember, like and subscribe, and we will see you next time. Thank you very much.
Real quick, hold on.
Oh, sorry.
We are growing fast. We have a whole slew of open positions right now. If this looks like something that somebody is interested in being part of, please go to our website and check that out.
Absolutely. Thanks again.
Bye.